The necessity and practice of selective coordination down to the instantaneous range for emergency systems varies depending on the specific facility and engineering requirements. The National Electrical Code Article 517 requires selective coordination for emergency systems, but does not explicitly state that coordination must extend into the instantaneous range. NFPA 110 recommends selective coordination down to the instantaneous range for vital electrical loads such as emergency lighting and life safety systems. Typically, selective coordination to the instantaneous range is considered best practice for emergency systems for the following reasons. Firstly, increased reliability. Instantaneous tripping can prevent faults from propagating and damaging critical equipment, ensuring continuous operation of emergency systems. Secondly, enhanced safety. Faults that occur in the instantaneous range can release significant energy, posing a hazard to personnel and equipment. Selective coordination limits damage and prevents cascading failures. Thirdly, reduced downtime. By clearing faults quickly, selective coordination minimizes downtime and ensures a rapid resumption of emergency services. The Florida Agency for Healthcare Administration standards do not explicitly address selective coordination down to the instantaneous region. However, they do require that emergency systems be designed to minimize the potential for cascading outages. This implies that selective coordination should extend into the instantaneous range to prevent faults from propagating and causing larger outages. Coordinating time current curves down to the instantaneous range requires careful consideration and analysis. The following steps are typically involved. Firstly, identify critical equipment. Determine the loads that are critical for emergency system operation. Secondly, establish target clearing times. Set appropriate clearing times for each critical load based on its importance and the potential consequences of failure. Thirdly, plot time current curves. Plot the time current curves for all protective devices involved in the emergency system. Fourthly, analyze coordination. Ensure that the curves coordinate such that the fault will only clear at the point closest to the fault without affecting other critical loads. Fifthly, adjust settings. If the curves do not coordinate properly, adjust the trip settings of the protective devices until selective coordination is achieved. Selective coordination down to the instantaneous range for emergency systems is often necessary to enhance reliability, safety, and minimize downtime. While the Agency for Healthcare Administration standards do not explicitly mandate instantaneous coordination, they imply the need for it. Engineers should carefully consider the benefits and challenges of coordinating time current curves into the instantaneous range and design systems that meet the specific requirements of the facility and applicable standards. For a deeper dive, let's explore the technical aspects involved in achieving selective coordination, particularly within the instantaneous range, focusing on the interplay between different protective devices and the specific requirements dictated by relevant codes and standards. Selective coordination is a fundamental concept in electrical system design, ensuring that in the event of a fault, only the protective device closest to the fault trips, isolating the problem while allowing the rest of the system to continue operating. This is particularly crucial in emergency systems where continuous power is essential for life safety and critical operations. Achieving selective coordination requires a thorough understanding of the time current characteristics of all protective devices in the system, including fuses, circuit breakers, and relays. Time current curves, or TCCs, graphically represent the operating time of a protective device for a given fault current. By plotting these curves for all devices in a system, engineers can visually verify that coordination is achieved, meaning that the downstream device always trips faster than the upstream device for any fault current level. The instantaneous range, typically defined as less than 0.167 seconds, or 1 cycle on a 60 Hz system, presents unique challenges for selective coordination. In this region, protective devices are designed to trip almost instantaneously in response to high fault currents. This rapid response is essential for limiting the magnitude and duration of fault currents, thereby minimizing damage to equipment and reducing the risk of electrical hazards. However, achieving selective coordination in the instantaneous range can be difficult due to the inherent tolerances and variations in the operating characteristics of protective devices. Several factors can affect the time current characteristics of protective devices, including manufacturing variations, temperature, and aging. These factors can cause the actual tripping time of a device to deviate from its published TCC, potentially compromising selective coordination. To address these challenges, engineers often employ a combination of techniques, including selecting devices with narrow tolerance bands, dirting devices to account for temperature variations, and performing detailed coordination studies using specialized software tools. Coordination studies typically involve simulating various fault scenarios and verifying that the protected devices operate as intended under all conditions. In addition to these technical considerations, it's also important to be aware of the specific requirements for selective coordination in emergency systems as outlined in the National Electrical Code and NFPA 110. As previously mentioned, the NEC Article 517 requires selective coordination for emergency systems but does not explicitly state that coordination must extend into the instantaneous range. However, many engineers interpret this requirement to include the instantaneous range, particularly for critical loads such as emergency lighting and life safety systems. NFPA 110, which provides standards for emergency and standby power systems, recommends selective coordination down to the instantaneous range for vital electrical loads. This recommendation is based on the understanding that instantaneous tripping can prevent faults from propagating and damaging critical equipment, ensuring continuous operation of emergency systems. When designing emergency systems, it's also important to consider the specific requirements of local codes and regulations, such as the Florida Agency for Healthcare Administration standards. While these standards may not explicitly address selective coordination down to the instantaneous region, they often require that emergency systems be designed to minimize the potential for cascading outages. This implies that selective coordination should extend into the instantaneous range to prevent faults from propagating and causing larger outages. In practice, achieving selective coordination in the instantaneous range often requires the use of specialized protective devices such as current-limiting fuses and circuit breakers with adjustable instantaneous trip settings. Current-limiting fuses are designed to rapidly interrupt high-fault currents, limiting their let-through energy and protecting downstream equipment. Circuit breakers with adjustable instantaneous trip settings allow engineers to fine-tune the tripping characteristics of the device to achieve selective coordination with other protective devices in the system. When selecting protective devices for emergency systems, it's important to consider their performance characteristics, reliability, and maintainability. Devices should be tested and certified to meet relevant industry standards, such as those published by Underwriters Laboratories and the Institute of Electrical and Electronics Engineers. In addition to selecting appropriate protective devices, it's also important to ensure that the electrical system is properly designed and installed to minimize the risk of faults. This includes using high-quality wiring and components, providing adequate overcurrent protection, and implementing proper grounding and bonding techniques. Regular maintenance and testing of protective devices are also essential for ensuring their continued reliability and performance. Protective devices should be inspected and tested periodically to verify that they are operating within their specified tolerances and that they are properly coordinated with other devices in the system. In summary, achieving selective coordination in the instantaneous range for emergency systems is a complex but essential task that requires a thorough understanding of electrical system design, protective device characteristics, and relevant codes and standards. By carefully considering these factors and employing appropriate techniques, engineers can ensure that emergency systems operate reliably and safely, providing continuous power to critical loads during times of need. Furthermore, it's important to emphasize the economic implications of selective coordination, especially in the context of emergency systems. While the initial investment in sophisticated protective devices and detailed coordination studies may seem significant, the long-term cost savings associated with reduced downtime and equipment damage can be substantial. Consider a scenario where a fault occurs in an emergency lighting circuit without proper selective coordination. The resulting cascading failure could shut down the entire emergency power system, leaving a hospital or other critical facility without essential lighting and life support equipment. The financial losses associated with such an event, including lost revenue, equipment repair costs, and potential liability claims, could easily outweigh the initial investment in selective coordination. In addition to the direct financial costs, there are also indirect costs to consider, such as the impact on reputation and customer satisfaction. A facility that experiences frequent power outages due to poorly coordinated electrical systems may suffer damage to its reputation, leading to a loss of customers and revenue. Conversely, a facility that demonstrates a commitment to reliability and safety through the implementation of robust selective coordination practices can enhance its reputation and attract new customers. Moreover, selective coordination can also contribute to improved energy efficiency. By minimizing the extent of power outages, selective coordination can help to reduce energy waste and lower utility bills. Efficient electrical systems that are prone to cascading failures often consume more energy than well-designed and coordinated systems. In addition to the economic benefits, selective coordination also offers significant environmental advantages. By reducing the risk of equipment damage and failures, selective coordination can help to conserve resources and minimize waste. The manufacturing and disposal of electrical equipment can have a significant environmental impact, so extending the lifespan of equipment through proper protection can help to reduce this impact. Furthermore, selective coordination can also contribute to improved safety in the workplace. By minimizing the risk of electrical hazards, selective coordination can help to protect workers from injury and death. Electrical accidents can have devastating consequences, both for the individuals involved and for the companies that employ them. Implementing robust selective coordination practices can help to create a safer work environment and reduce the risk of these accidents. To further illustrate the importance of selective coordination, consider the example of a data center. Data centers are critical facilities that house vast amounts of sensitive information and require continuous power to operate. A power outage in a data center can have catastrophic consequences, leading to data loss, system downtime, and significant financial losses. Selective coordination is essential for ensuring that the emergency power system in a data center can seamlessly take over in the event of a utility power outage. Without proper coordination, a fault in one part of the system could trigger a widespread outage, crippling the entire data center. In conclusion, selective coordination is a critical aspect of electrical system design, particularly for emergency systems. While the initial investment in selective coordination may seem significant, the long-term benefits, including reduced downtime, equipment damage, improved safety, and enhanced energy efficiency, far outweigh the costs. By carefully considering the technical, economic, and environmental aspects of selective coordination, engineers can design electrical systems that are reliable, safe, and sustainable.